Hello, this is the first lecture of my video series for the paper Data Communication Systems bearing course code ECE 702T. This is the course for the 7th semester students. The contents I am going to discuss here is the basic block diagram of the communication system, overview of digital communication system, and then synchronous data transmission and asynchronous data transmission. So let me define first what's communication. A communication is the transmission of information from the source to the destination or the user. So this information can be an analog signal or it can be a digital signal. If it is analog signal, we need an analog modulation techniques. And if it is digital signal, we need a digital modulation technique. Accordingly, we can have analog communication or we can have a digital communication. So this is the general block diagram of a communication system where there is a source with the transmitter which generates the information, and there's a user at the receiver end which receives the information. So what's information? And information is a data which the user at the receiver did not possess prior to communicating with the source. So therefore the key concept is the fact that the data which the user receives was unknown to the user before the source began communicating. So we have a source. So source is actually it's the originator of information. It originates the information. Okay. The source may be a human voice. It may be a speech signal. It may be any music. It may be a digital signal as well from PCs. So the user at the receiver end is the recipient of the information. The channel in between the transmitter and the receiver is a physical transmission media actually, over which the communication is sent. This channel can be, it can be a set of wires, it can be radio airways, it can be fiber optic cable, it can be twisted pair cable, etc. All channels have physical limitations. That means they can distort and attenuate the transmitted signal, and which will add noise to the transmitted signal. So therefore the received signal at the user end is not the exact replica of the signal generating at the source, right? So we need to have some error correction and detection techniques over there. So now what's transmitter? What's the role of transmitter? Since we could try to send the source output directly from the source to the user through the channel, but generally speaking the channel will add unacceptable amounts of noise and distortion to the signal. So in order to overcome some percentage of noise and distortion, we use transmitter to reformat and reshape the signal so that the channel will not distort it as much, although there may be some effect of noise, but that effect is very minimum, very less. After reformatting and reshaping, the transmitter may also boost the power of the signal. There can be the modulator inside the transmitter. If the source generates the analog signal, there can be the analog modulator in the transmitter. Otherwise, if the source generates the digital signal, there can be the digital modulator at the transmitter side. Now the receiver, what the main job of the receiver is that it attempts to translate the received signal back into the original information sent by the source. So this basically involves two steps. One is to compensate for the noise and distortion added by the channel previously, and another is to undoing the shaping and formatting from the transmitter. There can be the demodulator, there can be the analog demodulator for analog signals, or there can be the digital demodulator. So this is the general block diagram of digital communication system now. Here the information source is with input transducer. Input transducer change the non-electrical signal into the electrical signal, and the output of the information source here is the digital signal. rather than the analog signal. The transmitter part here is source encoder, it is channel encoder and the digital modulator. And the receiver part here is the source decoder, channel decoder and the digital demodulator. The main job of the source encoder is to represent the incoming digital signal by efficiently fewer number of bits, right? So we can see here in digital communication we convert the signal from source into digital signal. The point to remember is that we should like to use a few binary digits as possible to represent the signal. So this efficient representation of the source output results in little or no redundancy. The sequence of binary digits is called information sequence. So the source encoder is actually a data compressor over there. It represents the number of bits with some other number of bits efficiently. Since we can write the process of efficiently converting the output of analog or digital source into a sequence of binary digits is known as source encoding. There's a source decoder at the transmitter side. The main job of the source decoder is to do the reverse job of the source encoder. So at the end, if an analog signal is desired, then source decoder tries to decode the sequence from the knowledge of the encoding algorithm at the transmitter, right? So which results in the approximate replica of the input at the transmitter end. Then we have a channel encoder and then we have channel decoder. Since the information sequence is passed through the channel encoder, the purpose of the channel encoder is to introduce in a controlled manner some redundancy in the binary information in order to overcome the effects of noise and interference encountered through while transmission through the channel, right? If we have say k bits of information sequence and mapping is done from k bits to n bits, right? If k bits are represented by n bits, these n bits are known as code words, right? The amount of redundancy introduced is measured by n divided by k then, and its reciprocal k divided by n is known as the rate of code or code rate. Then at the receiver there's a channel decoder. The main job of the channel decoder is to remove the redundancy which has been added in the channel encoder at the transmitter side, right? We can have a digital modulator, as I said earlier, and we can have digital demodulator. In coming lectures, you will see we will discuss what are the digital modulation techniques and what are the digital demodulation techniques, right? So the second topic, this is asynchronous and synchronous transmission. Since when signal is transmitted from a transmitter and then when it is received by the receiver, there can be the timing problems between the two. That means between the transmitter and the receiver. Okay, these timing problems can be, there can be two solutions for these timing problems. One, you can have asynchronous transmission, and second, you can have synchronous transmission. Asynchronous transmission is when you transmit the data character by character, that means one character at a time, and the length of the character should be 5 to 8 bits. Within each character, timing needs to be maintained. Therefore, there should be resynchronization with each character. As I have here start bit, therefore in an asynchronous transmission with each character we need one start bit at least, and we need 1 or 2 stop bits. and there is p bit over here. This is the parity bit. This parity bit can be, this can be odd parity over here, or this can be even parity. This is used for the to check the error correction and detection. Okay, if there is a unpredictable time interval between the two characters, it can be shown here by this pulse. Okay, this is 8-bit asynchronous character stream. So for at least 8 bits to transmit, that means one character to transmit at a time, we need at least 3 bits more: one start bit, one stop bit, and one parity bit. So in an asynchronous transmission, the interval between the characters should be uniform. It's uniform. That means length of stop element. Okay. In idle state, receiver looks for transition 1 to 0. If there is a transmission, then samples next 7 intervals, character length, right? Then looks again for next 1 to 0, and the next character again, and so on. It's simple because the serial transmission is there. It's very cheap, right? Overhead of 2 or 3 bits per character is needed. That means 2 bits means 1 start bit, 1 stop bit, or 2 stop bits, and plus 1 parity bit, right? It's good for data with large gaps. That means in a keyboard we have a space like. And last, there's a synchronous data transmission. For synchronous data transfer, both the sender and receiver access the data according to the same clock. There should be same speed between the sender and the receiver. Therefore, a special line for the clock signal is required. A master or one of the senders should provide the clock signal to all the receivers in the synchronous data transfer. That means they should go synchronously with each other, right? Therefore, the block of the data is transmitted without start or stop bit. That means here, what's the main difference between asynchronous and synchronous data transmission? That means in an asynchronous transmission, we have one character at a time, but in a synchronous data transmission, we have one block at a time. To summarize, there are many serial data transfer protocols. Protocol is a set of rules governing for the transmission of data. The protocol for serial data transmission can be grouped into 2 types, one asynchronous and other synchronous. For asynchronous data transfer, there is no common clock signal, whereas for synchronous one, there should be same clock, common clock signal, right? Therefore, both the sender and the receiver in case of asynchronous transmission set up their own internal circuits to make sure that the data accessing is follows that agreement, right? But in case of synchronous transmission, the problem is solved by adding synchronization bits at the front, middle, or end of the data, which adds 50% overhead to it, right? Hence, it slows down the actual data transmission rate. Thank you.